Hello, all my colleagues. This is Dr. Ezi, and today we are going to tap on a very important topic that is very common in all types of exams, and it's about action potential. And as you know, everything that is happening in your body, a thought, a sensation, any neurological function, any muscular function is related mainly to action potential. So you want to understand this concept very well because it's going to help you have a good foundation for neuroscience. So let us move on and ask the very important question, what an action potential is. And actually, an action potential is a rapid, brief, and dramatic change in the membrane potential of an excitable cell like a neuron or a muscle cell. It's the way the nervous system sends information over long distances. There are two rules that you want to know about this action potential. The first one, to have an action potential, you have to reach the threshold. This is the first point. And usually the threshold is about minus 55 millivolt. Second thing, there is something called all or none law or all or none principle. And this principle means what? It means that if the action potential already started, it has just started. It doesn't matter how much that effect or that stimulus, how much is strong, how much it's weak, the action potential is propagated and it's going to move on. The second thing is that if the stimulus is not enough to reach the threshold, no action potential is going to be propagated. So the action potential is either there or not. This is the all or none principle. So just to recap here, the definition is it's a rapid transient change in membrane potential. This is the definition of the action potential, and you want to know that it works in the excitable cells, mainly the neurons and muscle cells. The threshold for action potential to start is the firing point. It's minus 55 millivolt, and it works according to the all or none principle. This is a drawing that concludes all the events that happen in the action potential. So what we spoken about is the threshold point. You can see it here where we have minus 55. This is the threshold point. We are going to understand this further. So let's move on here to section 2. Who are the main players in the action potential? And actually, the star of the action potential is the ion channels. The real work is done by something called voltage-gated ion channels. And these channels open and close depending on the membrane potential. There are two types of voltage-gated channels here that you want to understand about. And those are, the first one is voltage-gated sodium channels. These open so fast and they close fast. You want to understand this point about opening fast and closing fast. Why? Because this will have a tremendous effect on the action potential itself. Let's go to the other type. This second type opens slowly. So they are responsible because of that of the repolarization, which we are going to know after a while. And there is something also called hyperpolarization, which makes the potential much less than the resting potential that it should return to. And this is because those gates close so slowly. You are going to understand this much better after minutes. This is a simple image that can show you some idea about the sodium channels and potassium channels, so you can build a picture in your mind. Well, let's move to section 3 now. The 4 phases of the action potential, and this is the core of this lecture. We have 4 stages of action potential. We are going to speak about them very shortly, and we are going to focus very well on them so you can understand them very well and you can answer your questions in the exams. So first one, and the natural one, is the resting membrane potential. And from the name you can understand that the cell is at rest at this moment. So before anything happens, the neuron sits at about minus 70 millivolts. So you want to understand that the resting membrane potential is generally minus 70 millivolts. Okay, so this is maintained mainly by potassium leak channels and the sodium potassium pump. So this is an MCQ question, that what maintains the action potential, the resting membrane potential, the RMP. What maintains this one? And the answer in this case here is number one, the potassium leak channels, and number two, the sodium potassium pump, or the sodium potassium ATPase. This pump constantly moves 3 sodiums outside of the cell and 2 potassium ions inside the cell. So you want to understand that why the resting membrane potential of the cell membrane is negative. And the reason for that is because this pump actually pumps more positive than it gets inside. So it pumps 3 sodium ions outside each time it picks 2 potassium ions inside. And this pump actually works by energy. It consumes energy because it takes those ions against their concentration gradient. So it brings potassium inside the cell while there is a lot of potassium inside. So it's against the concentration gradient, and it takes sodium outside again against its concentration gradient. So in this case, it's using ATPs, or energy. Each time an ATP gets hydrolyzed, this action happens. Let's see here in this diagram the resting membrane potential. So there is a red arrow here, and there is 70 written by a red pen here, showing you that where is the resting potential is. Okay, so we move from this point now, and actually this cell now is almost sleeping. To recap, the resting membrane potential is minus 70 millivolts. It depends on potassium leak channels and sodium potassium pump, or sodium potassium ATPase. It sends 3 sodium ions out and 2 potassium ions in. We are going to continue now to the second phase of action potential. And the second phase of action potential is called depolarization. To reach depolarization, something must happen, because now this potential, action potential, is propagated already. So you want to understand that there is a stimulus that influenced this membrane potential. This stimulus helped the membrane potential to reach to the threshold point, which was minus 55 millivolts, and from there depolarization starts. Okay, so once the stimulus pushes the membrane toward minus 55 millivolts, the activation gates of the sodium channels open. So if they ask you what is responsible about depolarization, it is the sodium channels. The sodium channels are responsible about the depolarization. So they open, and what is the ion responsible about depolarization? It's sodium. So the sodium rushes into the cell. As you know, the sodium outside of the cell is high, the sodium inside the cell is low. So the sodium rushes inside, and this is driven both by the concentration gradient and the electrical gradient, or they call it electrochemical gradient. And the inside becomes rapidly positive. You remember, we are coming from down. We are coming from minus 70 to minus 55, and now we have positive energy, positive sodium coming in, rushing inside so fast. So in this case, you know that it enters through these channels in a rate of about 10 up to 8, about 100 million sodium ions per second. Okay, so it rushes inside, it gets all inside positive, and what happens because of this is the shoot of the membrane potential up to about plus 30 millivolts. Okay, this image here, it's an approximate image that show you what's active in this case, and the sodium ions here are just rushing inside. The other drawing here is showing you the action potential itself. So what we mean is what is meant by this red bracket. Okay, it's depolarization. You see here it's starting from the threshold and shooting out. Once you see here, the stimulus is trying to take it from the resting potential slowly. Once it reaches the threshold point, it shoots immediately because of the rush of the sodium inside by using the sodium channels. The gates open and it shoots up to plus 30. So to recap regarding depolarization, there is an activation for the sodium channels, an opening of the gates. The sodium rushes in and it moves toward plus 30. Okay, let's move now to the third phase of the action potential. Now we finished the resting membrane potential, it's minus 70, and it happens because of the potassium channels leak and the sodium potassium pump. Depolarization happens because of the rush of the sodium inside. And now we have repolarization, the third phase, and this usually happens at the peak of the action potential, up there. So it reached the peak, it has to go down now. So from the peak down, this is called repolarization. So at the peak, sodium channels are now inactive. Okay, so at this point, and we are going to mention this at a later time in this lecture, these channels cannot reopen now. Okay, they cannot reopen during repolarization. So during this time, potassium channels finally open. So now at this point, the potassium channels are going to open. The potassium exits the cell. You remember the sodium rushed inside from the extracellular to the intracellular fluid through the channels, sodium channels. Now the potassium will start to exit outside the cell. But you want to remember that the potassium channels are slow. So as it leaks outside or goes outside through the potassium channels, it's going to take with it the membrane potential back downwards to the negative side. Why? Because you have positive ions leaving the cell from inside and going outside. So positive charge is going outside, so the membrane potential is going to fall. So this is repolarization. In this case here, as in this diagram, potassium channels are concerned, and you see in this drawing here with this red bracket on the right side, from the peak down, this is called repolarization. What is responsible about this? It's potassium moving outside of the cell through the potassium voltage gated potassium channels. Okay, so to recapitulate here, there is sodium channels in activation, there is potassium channels open or activation, and the potassium exits the cell. Okay, well, let's move now to the last stage of action potential, and this is called hyperpolarization, and this happens because of the slow closure of the potassium gates. This is the reason of it. So as we have mentioned, because potassium channels close slowly, they open slowly, they close slowly, so the membrane becomes even more negative than the resting level. Why? Because more positive potassium is going to go outside, and in this case the potential is going to go below minus 70, and most of the cases it gets to minus 90 millivolt. This is hyperpolarization. So that the channels reset and the sodium potassium pump restores the minus 70 millivolt resting membrane potential. Okay, so after this going down, this drift down, the sodium potassium pump is going to work now. It's going to bring 3 sodium ions out and bring 2 potassium ions in. So it's going to reverse this process that led to hyperpolarization, and in this case the action potential is going to restore to minus 70 millivolt. Okay, so in this drawing here, this is the area with the circle, red circle, and the arrow where hyperpolarization happens. You see the resting potential line, it is here dotted line, and the graph here, or the action potential, is going below the resting membrane potential, leading to this phase, which is called hyperpolarization. To conclude this last phase, the potassium channels slowly start to close. Okay, and because of this downfall, the potential goes below minus 70, it reaches minus 90, and after a while, because of the action of the sodium potassium pump, the action potential returns to its resting membrane potential. Okay. Well, this image is going to give you a good idea about what's going on here. It's going to simplify this situation. So it's going to be more simple for you. So you have resting potential, depolarization, repolarization, and resting potential on the right side of the image here. Okay. So you see the in the drawing, the brown one actually on the right. You see out and in, this out of the cell, inside the cell. And we have this sodium potassium ATPase or sodium potassium pump. Okay, so this what returns the resting potential to its normal. Fine. So it keeps the resting membrane there to the normal, and after hyperpolarization it returns it again to the normal. Okay, so this is a resting membrane potential. It's kept by the sodium potassium pump. Well, depolarization, as I told you, you see at the last left one, this arrow going down, and in this case here sodium is rushing inside the cell. Okay, so in repolarization the sodium channel closes, the potassium channel works, and the potassium starts to go out, taking the positive charge outside. Resting potential actually again is going to be made after hyperpolarization by the sodium potassium pump. So it is sodium potassium pump, voltage gated sodium channels for depolarization, then voltage gated potassium channels for repolarization, and then back to resting potential. Okay, well, on the left side of this actually you can see the process in drawing. So it is here correlated with the action potential itself. So you will see the resting potential. Actually you are going to see the sodium is outside, potassium is inside, and the situation is stabilized by the pump. Okay, then after that you are going to see the next phase, which is depolarization. In this case sodium is rushing in through its specialized gates, and after that repolarization, the potassium now is going out of the cell. Okay, and in hyperpolarization actually the potassium is moving more out of the cell. The membrane potential is becoming more negative, and after that now the pump is going to work and return the potassium in, the sodium out in an unequal rate of 3:2, and the resting membrane potential of -70 is going to be maintained. So let's move now to section 4, and in section 4 actually we are going to speak here about what's called refractory periods. And refractory periods, what's meant by that, there is no action potential allowed here, and there are two types of refractory periods. One of them is absolute refractory period and the other one is relative. So regarding the absolute refractory period, during the early part of the action potential, when just the stimulus is there and we are moving to the threshold and the threshold has started, okay, once the action potential has started, okay, and after this shooting happens and after the sodium channels gets closed, okay, or inactivated, there is no stimulus. Even if this stimulus is a caterpillar, it is not going to trigger any action potential at this time. Okay, so this is absolute. No action potential can be propagated here. Once the threshold happens, because of the rush of these sodium ions through the channels and shoots up to +30 until the first third of repolarization, there is no action potential. Okay, so this is absolute. Let's move to the other type, which is the relative refractory period. Actually, during hyperpolarization, the membrane is further from the threshold, you see, because it goes, the resting potential is -70 millivolt, and it goes below -70, maybe much, to -90. So it's so far away from the threshold point, which is -55. So maybe it's relative because maybe a stronger than normal stimulus can trigger another action potential, but it's hard. Okay, it could happen, but it is very hard. So these refractory periods actually, as you see, are essential because they make the action potential move in one direction. There is no confusion here. So the conduction is going to be very smooth. Well, now let's see here in this diagram the refractory period where it happens. And actually this one here which happens, this is the relative one, you see. So the dotted line here is at minus 70, and at the hyperpolarization point, this is considered a relative refractory period, okay? And definitely the absolute one is at the threshold point. From the threshold up to the peak and down about third of repolarization, there is no action potential. This is absolute. So in the absolute refractory period, there is sodium channel inactivation. Already the sodium did its work and made the depolarization, okay? And this in the absolute. And in the relative type, actually, it happens, as I mentioned, in the hyperpolarization, and it needs a very, very, very strong stimulus to have an action potential. Let's move to another section. We are so close to the end, and it's about the propagation of the action potential, okay? So here we are speaking about the conduction itself, and as the conduction is going to move through the nerves, we have something called an axon in the nerves. So the axon is something long that connects the cells, nervous cells, okay? So it could be very long. So there are two types of axons, and one of them is called unmyelinated axon, okay? So the unmyelinated axons in this type, unmyelinated, so there is no myelin sheath. This is another lesson, okay? There is no myelin sheath there, okay? So the action potential spreads by depolarizing each neighboring segment of the membrane, okay? So there is actually expenditure of energy here. This is slow because the energy is not well directed in this case, and because every small section has to generate its own action potential, so the speed here seems to be very low, okay? Regarding the myelinated axons, here the conduction becomes much faster because the myelin sheath insulates the axon, and action potentials occur only at the nodes of Ranvier. Instead of traveling smoothly, they jump from node to node of Ranvier, and you want to know about these nodes of Ranvier. They are related to sodium channels and these things, so you want to know about them. But nodes of Ranviers are there, they in the myelinated axons, and they help in the fast conduction of the action potential through the axon, okay? They jump from node to node, a process called saltatory conduction, okay? So it is just fast. This diagram here shows two axons, okay? And those axons, one of them is myelinated, the right one, and the left one is not. So the right one is very fast. The left one actually is usually slow. To recap here, unmyelinated, it's a continuous conduction, okay, spreading all through the membrane. In the myelinated, it is saltatory conduction, and it depends on nodes of Ranvier. Let us move to the last point in this lesson, okay? And many people actually skip this part, but it is very important for you, at least to understand the general concept according to your stage. There are two equations that you want to know about. One of them is the Nernst equation. A Nernst equation, to understand it, and to understand, it is made to understand why the membrane potential changes the way it does, why the membrane potential itself changes. This is why you want to understand this equation. Why it changed from minus 70 to minus 55 to plus 30, and then goes down to minus 90, and then goes up to minus 70 again. Why? So the Nernst equation calculates the equilibrium potential for a single ion. So it takes sodium, for example, and works on it, and gives you the equilibrium potential for sodium. It takes potassium and tells you about the equilibrium potential of potassium, okay? So the electrical potential required to balance the ion's concentration gradient. It's what it's all about, okay? So this the equilibrium potential. The definition of an equilibrium potential for a single ion is the electrical potential required to balance the ion's concentration gradient between the two sides of the cell membrane. So for sodium, the equilibrium potential is around plus 60 millivolts. if you use this equation, it will come to you that the equilibrium potential is about plus 60 millivolts. So that's why when potassium channels open, the membrane potential rushes toward the positive side, up. So it shoots up, it reaches plus 30, and then it starts to go down. So for potassium, the equilibrium potential is down, negative, so it's minus 90 millivolts. When potassium channels open, the membrane potential moves back down to minus 90 millivolts. This is the reason why sodium is responsible about depolarization and shooting up, because its equilibrium balance is positive, 60 plus 60, and why the repolarization is the job of the potassium, because it takes everything down toward its equilibrium potential of minus 90. These values explain the shape and direction of the action potential. So this Nernst equation is going to help you understand why the shape of the action potential is like that. And this could be the most important graph in your medical life, especially if you become a neurosurgeon or neurophysician or something like that. Okay? So here in this page, this is the Nernst equation, just for your notice if you want. To conclude here, the equilibrium potential of sodium is plus 60 millivolts. You want to know that. The equilibrium potential of potassium is minus 90 millivolts. And this is the driving force, or these are the driving forces that explain the shape of the curve. Let's move now to the other equation. And this is the last point in our lecture today, and it's called Goldman-Hodgkin-Katz equation. They make an abbreviation for this equation as GHK. Okay, so the GHK equation is used to calculate the actual membrane potential at rest. It's a complicated one actually, but it's used for the resting membrane potential. It takes the equilibrium potential of sodium, potassium, and chloride and weighs each one according to how permeable the membrane is to that ion. You remember in the previous equation, Nernst equation, it's for each ion alone. But here it takes all these, and the permeability is the key here. So at rest, the membrane is far more permeable to potassium than sodium. So that's why there is potassium leak at resting membrane potential. You remember the resting membrane potential is kept there at minus 70 by the leakage of potassium and by the sodium potassium pump. Okay, so the GHK equation gives a membrane potential close to potassium's equilibrium potential, which is about minus 70. Why? Because this is the leaky ion. Its equilibrium potential is minus 90. So the resting membrane potential is minus 70. That is why. So this is the job of this equation. So this your equation here. Okay, and just to recapitulate, this equation is weighted by permeability. This is the major thing here. Okay, and there is high permeability for potassium, and because of that, the resting membrane potential is about minus 70 millivolts. So just to have a short conclusion for these equations, when you combine them together, okay, and with that you combine the behavior of voltage gated channels, you get a complete and quantitative explanation of the action potential. So now you understand the action potential, you understand the reason why it is like that. So this is the foundation for the neurophysiology, and mastering it will help you understand every higher level topic in the nervous system. At this point here, we are looking at the action potential again, drawn by hand, and now you know all the parts. You see here is the potential difference in millivolt, and this is the time in milliseconds down. Okay, so we have here the minus 70, and this membrane potential is at rest here at minus 70, and here we have a stimulus. So while it is at rest, something bothered this membrane, and what happens here is it started to raise up from minus 70. Once it reaches minus 55, this is the threshold, depolarization starts as sodium channels start to allow the sodium to rush fast inside, and this leads to the shoot of the graph up of the potential to plus 30. Okay, so a lot of sodium positive inside leads to more positivity inside, and this raises the membrane potential. So now we are at the peak, you remember, at this point, and while we are moving down at repolarization, okay, about third distance, there is no action potential else going to happen at this membrane now, and this is an absolute refractory period. So you go down from plus 30, repolarization is going on, but it happens because of the opening of the voltage gated potassium channels, and in this case here, those are slow, not like the sodium ones, and it moves down and down and down as the potassium leaks outside through the channel. And because it is slow to close also, it continues to release the potassium outside, so more positive ions go out, more negativity happens inside the cell, the membrane, and in this case here, it exceeds the minus 70 and goes down much negative to minus 90. Now it closes, and the resting membrane potential is maintained now by the action of the sodium-potassium pump. So this is the conclusion of the action potential. If you like this lecture and you want to support us to introduce much more information, this detailed in this way, that can help you to pass your exams and understand better about your career, you can subscribe now. This is the greatest support that you can do for us. Thank you very much. See you in the next video.